degrees. Quick reminder, the best one that I can give you of what 1 radian, not pi, but what 1 radian is. 1 radian is an angle that intersects a circle in the same arc length or an arc of the same measure as a radius. So whatever the radius is, if you were to make a ruler, a flexible ruler of tick marks of a radius, however big or small a circle is. If you were to make a ruler with tick marks of the radius, and then you were to fold that around the circle, where the 1 would hit would be 1 radian, where the 2 would hit would be 3, where the 2 would hit would be 2 radians, where the 3 would hit would be 3 radians, and it wouldn't quite be a full half circle because how many radians would we need?
3.1.
3.141596. And so I want you to think of pi as in the Greek letter, as in the mathematical notation, which is only half a circle to be a calzone, 2 pi to be the whole piece of pie, or 3 calendars pi, or quiche, or whatever else circular you want to think about that is edible, or something that's non-edible as well. It's breakfast-ish. I felt weird just using pizza and calzone. And
Omelet.
An omelet.
They're not.
They fold them. Depends how you do omelets. All right. How do we find, well, first of all, geometry. You're welcome, SAT stuff. Not that it's really that much SAT stuff. But what is true if 2 angles are complementary?
They equal 90.
Okay, give me the unit. Some of you did, some of you did not. They add to 90 degrees, or what would be equivalent to 90? Wait, how much of a half circle is 90 degrees? It's a quarter of a full circle, or it's half of the calzone, so it'd be pi over 2, right? Pi is the calzone, cut it in half, pi over 2, no big deal. Okay, add, why am I doing this? If I gave you guys a unit circle quiz on Friday, how many of you would have aced it?
No.
How many of you would have been able to at least fill in angles? All the angles. Okay. If we look around, we didn't remember it from last year. I need you to remember it for next year and the years following, at least as long as you're in any sort of math. Okay. Come back. In high school, it's optional. In college, it's not. Depending on how well you do in a placement test, those can be hard. They might send you back to geometry, so we're trying to learn as much now. It's rough. It's a rough world out there. There are good parts, but there are rough parts. So we're going to do the best we can, okay? Coming back. Adding to 180 degrees or adding to pi over 2. Complementary. Are those equivalent?
Yeah. No.
What should be there?
90.
Thank you. What was I thinking when I wrote 180?
Supplementary.
Exactly. Supplementary. Those add to 180. Or a full half circle, and a full half circle, a full calzone is going to be who?
Alright.
Got it. Don't judge. It is. That's ignorance. Okay, so, one quick question. One quick question. Before I get to like some good examples. Is there, I'm going to do a little example. I'm just going to do it in degrees to make it easy.
3 letters.
Is there a complement for 100 degrees? Some of you are like -10. And -10 would get it to be 90, but technically, if you went back to geometry, the definition of a complementary angle, or the complement to an angle, are we allowed to go negative? 80 would work, 80 and 10, 70 and 20, 35 and 65, 55, etc. In order to have a complement,
350.
Wow.
no. In order to have a complement, the angle has to be less than 90. And in order to have a supplement, what else do you think has to be true? Has to be less than 180. So we're not going negative. When we're doing complements, and supplements, it has to be less than the angle that we're adding. And if you think of it, you can say adding up to. We're adding up to. We're adding a positive angle. And if you can't add a positive angle to get there, to get to 90 degrees, not to get to the same placement. That would be coterminal, like the page that we talked about on Struggle Friday. We're not talking about other ways of getting there with big old numbers. We're saying just to get 90, just to get 180, we have to have an angle less than that. Okay. So let me go ahead and give you a few. Ready? What if I was to give you, let's do letter A, find a complement and supplement to a I haven't put in the graph yet. Let's do 63 degrees. Letter B, different colors. What if I was to give you 5 pi over 12. Ooh, that's fun. Now letter C, what if I was to give you 2 pi over 3? Okay. I'm gonna let you start easy with degrees. I guess technically you could use a calculator. Maybe you could do it without a calculator. Start with the degree one. See how much you can get of the radian one, and then we'll come back and then see how far you guys get. And go the rest of the way, Ricky.
Are we finding both?
Both.
Okay.
The complement and the supplement. I'm just going to label them C and S if that makes sense. Maybe you can't get all the way, but that's okay. Get as far as you can. Complement. Come on, the degree one you guys should be golden on. Maybe you don't like the number. Maybe you have to grab out a calculator and cheat a little bit, but you should know what to do. Subtract. Just in case it helps, the first thing to knowing whether or not it's even legal to fund. I'm approximating, it's probably a good approximation. Better like a third or 2/3. Just to see if it's legal, question. Is that going to have both a complement and a supplement? Yeah. Why? It's less than 90 and less than 180. Okay. Ryan, you find me the other piece. Subtraction. What do you guys get for the complement? Not saying if you don't all, what do you get for the complement? 27. If you're like, wait, how? Just look. If it's adding up to 90, I subtract from 90 and say, who's left? Supplement? What's the math? You get it? Don't tell me the answer yet. If it's adding up to 180, then I subtract from 180, right? If you think about it, it's 27 and a whole nother what? 90. So I could just do 90 plus 27 if I want these 50, or I could subtract it. And I end up with? Okay, some of you mental math is harder than others, but do we at least get the idea in degrees? Take away from 90, take away from 180. Simplify, simplify. Good? What's going to change when we come down to B? First of all, is B legal?
Yes.
Can I find why? How do you know for sure?
Because it's less than 90.
How do you know it's less than 90?
Take 5 over 12.
5 over 12 as a fraction is less than what? Well, you could do it in your calculator. What is 5 over 12 in your calculator? Real quick.
Like 4.
Okay, 0.41. Is it less than 1/2 0.5 pi? Yeah, it's 0.41. It's okay. How else can you know that? What would 1/2 pi be in 12ths? How many slices? 6 over 12, right? Okay, so this is less than 6 over 12. It's less than pi over 2. It's pretty stinking close. We'll put it like here-ish. But still, 5 pi over 12 is legal, right? What would the math be to take away or to subtract to get the complement for 5 pi over 12, which is in radians? you would take the pi over 2 instead, and you would subtract 5 pi over 12. Now, how many of us can do that off the top of our heads? Just with it the way it is in our mind. Not many. Not many. But if you think what they said a second ago, how many twelfths is 1/2? Well, if there are 12 pieces equally cut and you have half of them, how many pieces do you have? 6. Or if you multiply top and bottom by 6 to get 12, if you think about this as 6 pi over 12, well, how much easier is it now? With 6 twelfths, take away 5 twelfths. 1/12. And remember, that's a pi. Don't be scared of fractions. We just have to figure out a way to master them and work on them. The 1/2, yeah, that was rough, but the 6 twelfths, ouch. 6 pi over 12 minus 5 pi over 12 is 1 pi over 12. Now what are we going to do when we come down to supplementary? What's the big idea? Pi, not a 1/2 though. Okay, you could, sorry, Tyler's like, well if that's pi over 12, you can add a half pi. That's one way. The big idea is you're saying pi take away how much, right? So that's the big idea. We're just following the formula. There is a trick to it. But guys, if you have the whole pie, the whole calzone, question, how many slices do you have if it's cut into 12s? You have all 12. So 12 over 12, right? Multiply by 12 over 12. What's 12 minus 5? 7. Or if you use Tyler's trick of take the 1 pi over 12 and add the other half, the 6 pi over 12, you also get 7 pi over 12, right? I want you guys to take a second. Some of you finished letter C and some of you didn't get to it. Try to take what we just did with 1 in radian and try to apply it to what you guys are doing. Try to apply it to letter C when you finish it. Don't forget to first ask yourself the question, is it legal to have both? Legal to have both. Okay, real quick, check in your groups. Just because some people might be struggling with the math and others, you know the fractions and you can help. Collaborate real quick.
I think it is.
And if something is illegal, maybe talk it out.
Yeah.
Yeah, 2/3.
I mean, 1/3.
Pi minus. Yeah. What do you guys think? Is it legal? Why not complementary? Where's 2 pi over 3? Calzone, 2/3. Uh-oh. 2/3 if it's over here, right? So you have a 1/3-ish and a 1/3-ish. Remember, if you're doing fourths, you can cut in half and in half. How many of you guys cut a pizza? Please say.
Oh.
That's it? We can get you some life experience. Get some pizzas and pizza cutters in here. Anyway. If you're doing 2/3 of a half circle, it'd be over here, right? What has he passed?
1/2.
He's past 90. So no complement. We'll say none. I know, some of you started going. And if you were going, wouldn't you have gotten a negative number? And when you get a negative number, you're like, oh, I missed it. It's none. Right? Now, supplement, what are we going to do? He's definitely good. 180 minus, but we're in radians. So what are we going to do? Pi minus. This is what Honors and I were doing during that fire drill last week. Anyway, question. No, literally, we were changing common denominators. How do we subtract this? Either logically say, okay, well that's 2/3. What's left? 1/3. Or can you really clarify the fraction, but say, no, I got this. Multiply top and bottom by 3 because he's over 1. What's 3 pi minus 2 pi all over 3? That's it. We got it?
Not really, sure.
Is the math thing?
Yeah.
Okay.
Usually.
Tyler was
I'm just afraid of that reaction.
Oh, you didn't? Awesome. Well, I was just trying to help those that don't logically see the 2/3 is what we have, 1/3 is what's missing. Because you can take pi, okay, focus on it. Pi over 1, I got a common denominator. Does that make sense? And then I went ahead and subtracted to make the fractions easier. Any other questions on complement supplement? Going once. Going twice sold. Did I go all the way down? Oh, struggle. I went to the end of the chapter. Let's not go to 4.8 right this second. Yeah, that was intense. Now, when I asked the question, and I made you guys do math, like pi minus or pi over 2 minus, and I made you do that, some of you were like, oh, can't we just go to degrees and use 90 and 180? And the answer is yes. We just hadn't talked about this page yet, and I made you struggle through the fractions a little bit because I think that that's actually more useful as you go on to actually have an ability of working with fractions because they're much more practical. You don't have like cups of ingredients in decimals. That's awkward. That's weird. If you did, it'd be 0.66666666 as a cup, but that's just what? Or 0.3333. No. So fractions are practical, but even though fractions are practical, there still is a place and a time for figuring out what radians are in degrees and figuring out what degrees are in radians. And if you guys have realized from what I've been talking about with the whole, hey, the units make the difference as to what we're talking about and how 3.1415926 can equal 180. The numbers don't, but with the units they are equivalent. We're building up to bridges. To get rid of what we don't want. Or to get what we do want. That's a more positive spin. Anyway, either way. We've already talked about radians. Radians make a ruler with tick marks of the length of the radius and then wrap it around. That's what a radian is. However, what's a degree? Well, to be honest, even though he's a thing that you're more used to because you've seen him for longer with protractors coming out, I don't know, when you were like in 6th grade math, maybe 7th, 8th, they start using compasses and protractors. Somewhere around there, right? Oh, no, true. Oh, holy cow. Okay, long time ago. Anyway, what is a degree? A tick mark on a protractor? Okay, you're right. But what is 1 degree? Well, he's 1/360th of a rotation around. That's so awkward, right? The radian makes a lot more sense, at least spatially, to say, okay, it's the radius, and then you wrap it around the circle, and that's 1 radian, or 2 radii wrapped around the circle. Okay. But a degree, it's 1/360th of a rotation. Good thing they didn't teach you the first time that you used a protractor what that was. It is something, but it's not the best, especially when we get into formulas where you need radians. Because you need the idea of the arc length, not the idea of a little rotation thing. So anyway, how do we convert back and forth? Dimensional analysis. How do you do dimensional analysis? Hopefully a lot of you guys have already seen this in, what is it, 10? Isn't Mrs. Leon in those bridges? Multiplying by 1 creatively to cancel units. Mrs. Leon, she's a champ. But yeah, she is. She'd do my job any day if only she had more time. Okay, coming back. Degrees to radians. She could do anyone's job in the math besides. Coming back. Degrees to radians. If we're starting, now I'm going to have to make some sort of variable, I don't want to give you a number, I want to give you a formula. And to do that I have to make a variable. Okay, can I do x? X degrees. If I started with degrees, I would have a degree mark. If I started with radians, guess what? No degree mark. That's literally the difference, and that's what's super confusing. Radians, sometimes they have pi, but sometimes they're just numbers. You just have to notice that they don't have degree marks there in radians. Now, if I want to go to radians, I have to build a bridge over angles. Please no. The Lord's kind of cute. But ha ha ha. Okay, coming back. Coming back. Where did I put the degrees?
On the bottom.
You have the degrees, John, not you. The degrees. There we go. I need the degrees in the bottom, so them to cancel out. And what I want at top, radians. Don't put anything, because radians aren't really seen. I'll show you what I mean in a second. So hold on. How can I make an equivalent statement? Okay, I'll put the radians just so you see it, even though it's an understood unit that's never written. Like when you tell people a command, go to the store, There's no subject, but what's the understood subject? U. Radians are the understood label that we never say or write. For question, what's the equivalent statement between radians and degrees? You could, not 1 over 180. Pi over 1. Good. I need something that's equivalent, like my 12 inches in 1 foot, 24 hours in 1 day, 52 weeks in 1 year. Pi radians and 180 degrees. Now remember, pi does not mean radian. Pi is just a common radian measure. It doesn't mean radians though. Radians is a little understood unit. What's going to happen when I multiply by this conversion unit, or conversion factor? Degrees cancel. And I end up with whatever is in the x spot times pi. I guess we would normally write it x pi, but since it's an x, usually we write pi x. And technically, tacked on, since there is no degree mark, will be radians. Now, we don't usually write it, it's understood. It's just kind of, since there's no degree mark, it's radians, but I'm showing you so that you can understand. Blake?
We call it like 360 for a circle. Like for degrees. Why is it?
You have a protractor, 180. To make a full rotation on a circle, you need 2 protractors. How many tick marks would there be? 360.
Or like why is it taking?
Oh, why have they made it 360?
Yeah.
To be honest, off the top of my head, I have no idea where degrees came from. It'd be a great thing to research though.
It should have done 1 tick mark.
Well, 1 tick mark? I don't know. You should just like the number 90 and say multiply by 4.
Sasquatch.
That's my guess.
Makes no sense. Hold on, focus. That's a really good question, right? I think someone should look that up. I think it'd be worth some sort of bonus. You just have to show me some sort of printout as to what a 3 and where it came from. Put your name on it, gets me wrong. So, radians to degrees, I'd be interested. What if, I didn't say only reward 1 person. So, if there is no degree mark, can I call radians? There's no degree mark, and it's talking about an angle that's in understood radians. I'm going to show it, here we go. Okay, in question. What am I going to put down here? Understood radians. And who goes along with understood radians? Pi, because the quick conversion, or the quick equivalent statement is pi is equal to who? And that way the little understood radians that you don't really see anyway, but that's alright, they go away. And we would end up with 180 times, sorry, pi's in the bottom, times x over pi. And sometimes x has a pi. So it's going to be all nice and pretty and it's going to simplify. However, sometimes it doesn't, and that's alright. So how do we get from radians to degrees? Multiply that by this puppy right here. And how do we get from degrees to radians? Multiply by that puppy right there. Do you really need to memorize these? I don't think so, because you're just going to do the math when you multiply. Ricky,
Why wouldn't the degrees to radians be over 180?
oh, good question. I have no idea. I got distracted thinking about greater things. Probably not. Okay. There we go. Is that better?
What?
No? Pi times x over 180, isn't that what would happen when you multiply? Because isn't x going to be over 1? And over 1? There we go. Word of the wise, what can you guys learn from the mistakes I fairly commonly make in class?
That everyone screws up.
When you try to multitask and you're doing something and you're distracted by something else, it doesn't always turn out so hot. What am I distracted by?
Us.
Talking and measuring how you're doing and then trying to think of where I'm going next.
Smart aleck.
Smart alecky. Wait a minute, we need to do some conversions. Hold on. Oh, you know what? This example will let us do a conversion. All right, hold on. Go ahead and write down the formula. The example makes us do a conversion, and I'll explain why in just 1 second. Get the formula down where you can see it. Okay. But this is an application problem. We still haven't converted. Hang in there. Is there anywhere else in notes, section 4.1, I know it's hard because it comes from Friday, and I formally wrote down then, where you saw the letters S and R and theta in any sort of order? Yes, but what was that formula? Yeah, the angle measure in radians equals S divided by R. Arc length divided by radius. Do you think the meanings of the variables have changed at all? No. So who's this still? Arc length. Who's R still talking about circles?
Radius.
And what's theta still talking about? And here's the struggle. Wasn't this the formula that we used to define radians? Theta is an angle, yeah, you're right, and angles can be measured in degrees or radians, but this formula was used to define radians. So for all these application problems, guess what? It's crucial that we have the angles in radians, or else they literally will not work. Because angles in degrees have nothing to do with arc length. That's not going to help us. But angles in radians are defined by arc length, so they will help us. What does that all have to do with how we need to practice our converting from degrees to radians or vice versa? In this example that we now have that says, you have a circle with a radius of 4 inches, find the length of the arc length, intercepted by a central angle of 240 degrees. What's the big deal? We're going to have to convert because this is not appropriate to the formula that we need to use. Because we need it in radians. So before you ever go plugging into your formula, you need to say, no. Good try. 240 degrees is not what I want. I want to know who you are in radians. Now, we could go thinking about how many slices in this, that, and a calzone, but to be honest, we're not going to be able to really do that. It'll be much easier just being able to convert with one of those nice conversion factors. So question, I have degrees. What am I going to multiply by that'll get rid of degrees and get into radians?
180.
Where's the 180 go though? On top or on bottom?
Bottom.
Good. Right? I need that to cancel out. But what's equivalent to 180 degrees in radians? Pi. And we don't have to write the little understood radians. We just need this degree mark to be canceled, and now it is. Now some of you that are more mental mathish, you're like, hey, the zeros can cancel because there's a 0 on top, 0 on bottom. Now we have 24 over 18. Any common factors there? 6?
6 over 3, which is 2.
6 goes into 24 4 times. 6 goes into 18 3 times. What was all of that for? To get a proper theta that can plug in. Okay? And then one more thing, kiddos. Is this really a new formula or is it just rearranged? So technically, we don't even need to necessarily memorize a new formula per se. It's just use the old one and say, okay, sweet. You could say theta equals S over R. You could plug in theta is 4 pi over 3 equals S. Do we know the arc length? So he stays alone. And then R is equal to what? 4 inches. We could write the formula like this and solve for S. Or, similarly, we could, I guess, memorize a new formula. And we could just plug in and say S is equal to who is R, 4, and who is our angle, 4 pi over 3. This is going to end up to be the same either way. Over here, how would you get S by itself? Some of you would say cross multiply. Oh, you're right, but I can get S by itself just by multiplying by 4. If I do one side, I do the other, and either way you cut it, whether you stick with the original formula or plug into the new rearranged formula, you end up with, well, careful. That's a 4 over 1, right? However you do it. You end up with S is equal to 16 pi over 3. What are we measuring in? What's our units for just the length?
Radians.
That's for the angle. We're in inches for the circle. Does that make sense?
Yeah.
So how long will it end up being? This many inches. And if you wanted to, I suppose you get a decimal. Blah. Stop there because that's a nice, perfect answer. Sound good? So if you have degrees and you need to convert to radians, which you will for any of the application formulas, you have to multiply by a conversion factor, get it to radians, and then go plug it in. But sometimes you might plug into one formula and then change. Sometimes you can plug into one variation of a formula and still get to the final answer without having to memorize another just rearranged version. Okay? What if, a few more things come up? What if a few more things come up? Now, guys, to be completely honest, these aren't going to be formulas that you're going to have to memorize for a quiz or a test. This is not the main point of trigonometry. However, being able to understand how to use angles, plug in angles, to solve for other things like in physics, this is mostly physics right now, is a practical skill. So we're just seeing how we can use it, even though physics is not necessarily the point of this chapter, but it is one of the main applications. Linear speed is equal to arc length over time. And this would be an example of something that's like traveling in a circular pattern, maybe like someone in a Ferris wheel car and how quickly they're going around a circle. Their speed, even though they're traveling in a circular path. There are problems where like a fly is stuck on a bicycle wheel or a tack is on a bicycle wheel. How quickly is it rotating? A kid on the outside of a merry-go-round, how quickly they're spinning. That's what linear speed is talking about. It's arc length divided by time. But we just saw there's another formula for arc length, so technically there is another way of writing this. Arc length is equal to r times theta. So we could also maybe not have arc length and have to find it and then divide by time. Depends on the problem. Angular speed. Ooh, that's a Greek letter, isn't it? What's the little weird W that's squished in at the top? Omega. Huh? Yeah, the V is another one. I just figured most of you wouldn't have noticed it until this one. And you're like, wait a minute, I think they're doing something. Anyway.
No omega.
Yeah.
Establish that.
Central angle. Uh-oh. Hold on, remember, in all of these, whenever you see theta with all of these physics applications, you need to be in radians. And if you're not, if you're in degrees, or if they give you degrees, you have to convert first. In radians. One quick hint, just because you might see this wording in homework, if you see something like 1 revolution, is equal to 360 degrees, but since we're trying to get into radians, it's equal to 2 pi radian. 1 revolution is 1 time around the circle. Just a quick little hint in case you see it. 1 revolution is equal to 360 degrees or 2 pi, just in case you need to convert. And then area of a sector. I haven't necessarily labeled anything in this formula, but do you guys know what the different labels are? What's A stand for?
Area.
Yeah. What's R stand for? Radius. And then beta is just the angle, the intercepted angle, the central angle, they could say it different ways. In radians once again. Are we almost there? Oh no, the screen's dying too. Maybe it's my computer.
Oh, it's been doing that all.
I think it's my graphics card. Oh, this is disgusting. I know. Because before I was able to figure out an online book. We need to talk about that, by the way.
We have an online book?
You had one for chapters 1 through 3. Sadly, chapter 4, things have changed a little bit. You want me to show you what I'm talking about? You guys have known the one that's online. You silly goofs. I showed it to you at the beginning.
No.
Oh my goodness.
I just left 2 paper copies.
Now hold on. Is there a dilemma?
A little bit.
Where have you found the book in the past? Good. On my website. And where did you find it under? We're talking about this for a very specific reason. Hang in there with me, even though the lights just went dark. This one. Helpful links, right? Boop.
Wait, I remember the...
Oh no. Online textbook? What? Okay. Now, has anybody realized the struggle with this online textbook? It only goes up to chapter? Oh my goodness, and it's still taking forever to load even with the chapter. Okay, hold on, we're letting it load, it's taking forever.
Play a game.
Playing a game? Did you guys play the Halloween game? That was fun. On Google? No? Never mind. Yeah.
Halloween game? What?
There was one on Google. You know how they had the special, they had a fun game with like ghosts or something. Anyway.
Like Pac-Man?
Okay, well now that I can't show you anything because our network stinks, who's playing games in a computer class? Anyway, it really does affect the rest of the campus. So, We can't really go over that. I'll show it to you as soon as I can. Is it still going? Oh, well, that's fun. Huh.
I guess that's the struggle with having it online.
Wait, maybe I cut in. Did I cut in? All right, well, I'll show you on this one because I actually have it downloaded. We'll do it this way instead. Okay, this is the one that was online for you guys to see, and somebody was like, hey, it only goes up through chapter 3, and what's the struggle with only going up through chapter 3 since we are in section, 4.1? Ah, stinks. So you guys have nothing?
Yeah.
We really have nothing. Yes, you can't do that.
This second you have nothing. However, let me show you. Now everything comes up all at the same time. Yay, there he is. But if I scroll down, yeah, it's not going to work. Hey, look, he's frozen. Let it go. Anyway, so
Good job, guys.
I'm going to show you what I have under honors because they've been in chapter 4 for a while longer than you have. Do you guys notice? Oh, wait a minute. In the classroom folder, because otherwise it's kind of illegal for me to do this if it's not in some sort of protected environment where I know exactly who's accessing it. I bought an online version of the book that you guys can access, the entire version. The problem is it's huge. Because the chapter 3, you guys see how long it took for the 3 chapters to load? How many chapters are in your book? 12. Struggle. Okay. So this is a good version, but when you click on it, I'm going to put it in your classroom folder so that you guys can access it too. I just have the classroom folder so that it's private, it's contained, and it's password protected, etc. When you click on it, guess what? So we can't access it?
Nope.
Do you guys see the 3 little dots up here? Oh. Okay, open a new window. Now it's going to work. Nope. Wait, so we can't access it? You could download it, or, wait, you should have some sort of open with selection. Now, maybe you don't have the ones that I do. Lumen PDF is a good one, but you should have the Connect More apps if you're doing it through Google Chrome. Long story short, it's too big for the computer to be able to show you as a preview. But if you do some sort of, ready, PDF viewer, you should be able to, right? You should be able to get one that works. Now, this one is a good one, 1,864. I know it's 3.5, but it still works really well, and it actually is a nice way to see the book. I'm just letting you know. Oh my word, you guys are snobs. Anyway, long story short, it'll work, okay? I'll upload that in your Google Classroom if you guys want to check it out and make sure you can access it tonight. You can. It's going to take a while. Anyway.
Or you can just bring the book home.
Or you can just bring the book home like all the amazing people. Okay, let's come back.
That's the third option.
That's no fun.
Yeah, or you can just take pictures of the book.
For right now, yeah, isn't that way easier? That's fun too. But just in case some of you have been using the online one, I didn't want you to think I was taking it again. All right, come back. Oh, you can't see it.
No, we can't. No, we can't.
Okay. I know, it's a horrible picture. I have a better version. I just didn't have time to get it up to Monday. Anyway. Listen, how do we find the angular speed? You guys just wrote down the formula. I'm sure your homework helped. How do you find angular speed?
Central angle. It's central angle over time.
Omega equals theta over t, right? What would that be measured in? Oh, they gave it to us. Radians per minute. What do we have right now? Did they give us an angle? No. Did they give us a time? No. What did they give us?
Revolutions.
And radius.
They gave us 4 revolutions per minute. Wait, 4 revolutions per minute. Didn't we just talk about revolutions a second ago? What does revolutions mean? 4. Maybe we're using dimensional analysis in another way as well. 4 revolutions per minute. What do I multiply by to get rid of revolutions and get to radians?
2 pi.
Yeah, 1 revolution is 2 pi radians. Look at that color pop. Anyway,
Oh,
did it work?
Yeah.
Revolutions would cancel, and I would have my angular speed. Hey guys, go ahead and get on out of here. I'll see you later. Homework is due tomorrow. We got a homework help in from the crazy world. Hi guys.